Good afternoon, everybody. I'm Americo Cunha from Rio de Janeiro State University. I'm assistant professor of applied mathematics. This work that I will present here has to do with a public health issue, the epidemic of Zika virus in Rio de Janeiro State, and was developed by myself in collaboration with my students, Herbert Dantas, Michel Tozini, João Peterson, Vinicius Lopes, which unfortunately is not here. The presentation is split in 4 parts: an introduction, then we present a model for the virus propagation, a procedure to calibrate this model with real data, and the final comments. So, Zika virus was a recurrent theme in the news in the last 12 months at least, especially here in Brazil. This virus, which is shown here in this picture, was first isolated in Africa in 1947 in Uganda. For curiosity, the name Zika virus was given during this time in honor to a forest, which is in Uganda. The vector of this virus, which spreads in the population, are the mosquitoes from Aedes family, which unfortunately for us is very common in several regions of Brazil. And in the last months, the Zika virus received several attention from the authorities, not only, but mainly because of the connections of the Zika virus fever with other more grave diseases, such as Guillain-Barré syndrome and microcephaly. Here I show a picture of the spread of the Zika virus in the world. It's not the most updated, it's from February of this year, but it gives an idea of how the virus is spread around the world. So it's not a local issue anymore, it's an epidemic in global scale. The first cases were reported in Africa several years ago, until some years ago. But after Africa, this was spread to Asia, and then to South America, Mexico, and more recently Australia and United States. All these cases here in Africa and Asia were reported prior to 2015, but in the last 12 months, the virus spread from this region here to other parts of the world. In the particular case of Brazil, you can see here the number of suspected and confirmed cases for this year. You see, in the first months of this year, we had a blow up in the number of cases here, so this became a relevant issue considering public health politics. I came from Rio de Janeiro State, and this state deserves special attention this year because we have a recurrent problem with dengue every summer, because Rio de Janeiro is a region so favorable to the development of Aedes mosquitoes. And we had the Olympic Games in the last month of August, which received many tourists from different parts of the world. And the epidemic there could be a potential source to spread the virus more and more in the world. So, motivated by this, we decided to study more the dynamics of this disease and develop a model for this. The objectives of this research are first, develop an epidemic model to describe the Zika virus propagation in Rio de Janeiro state, verify from the quantitative and qualitative point of view the capacity of prediction of this model, and then calibrate this model with real data in order to improve the predictions done with this model. I will discuss the model now to describe the interaction between the populations of humans and the population of mosquitoes which transmit the virus, we decided to use a SEIR model, which is a classical family of models in mathematical biology. But the particular interesting for this model is because it was used recently to describe the virus, the Zika virus epidemic in French Polynesia. This class of model splits the populations in 4 categories: susceptible, exposed, infected, and recovered. The human population and the vector population, 3 categories: susceptible, exposed, and infected. It's not considered as a recovered category for the virus because the time life of a mosquito, not for a virus, sorry, for the mosquitoes, because the mosquito time life is very short compared with human time life. So, in no sense, consider these small groups. The interactions among the groups is shown here in these arrows. And when we translate this biological model into equations, we arrived with these 8 ordinary differential equations, which involve 7 parameters. So our mathematical model for the is this dynamical system here. In this paper here, we found this model with parameters that were estimated and constructed to the Polynesia area. So the parameters of the model from that area for sure are not suitable for Rio de Janeiro because climate factors, population factors, etc. So the first step in this research was to describe suitable parameters for the model. As you can imagine, this is a very hard task because we don't find in books or in papers, or even if we wrote to choose some research in futures, or what's the value for the alpha of this model or beta. So the first step, and we lost so many time looking for papers, trying to find parameters that we can use, and some of them we found, others we used the critical sense to say, oh, this makes sense, no, this is not. After we plugged these parameters in the model, we obtained typical time series as this, for the number of susceptible humans, exposed humans, infected humans, and recovered humans. You can see the susceptibles decrease a little and then became stationary. The exposed and the infected, because someone exposed most of them will be infected after. We see this blow up behavior here. And the recovered, it's a curve which goes from 0. It has a very fast increase and then becomes stationary. For the mosquitoes, and here's the cumulative of the humans recovered. It's very similar to the recovered because almost all the people which was infected become recovered. For the mosquitoes, we have this typical time series here. For the susceptible, for the exposed, and for the infected. So, we have a model. We can predict the number of new cases each week. This is a prediction for the year of 2016. And we then look for a little in Google for the number of cases, and we discovered in Fiocruz site the number of new cases reported in Brazil, in Rio de Janeiro state, specifically. When was the first one? April. After April. And we see here the points do not agree with the model response. The model response is not predicting well the epidemic, the outbreak. And so, the mathematical model is not representative. What we need to go now? What we need to do to improve the predictions, calibrate the model. If you consider the mathematical model here, we plug initial conditions and model parameters, we obtain the model response. This is the direct problem associated with this mathematical model. But we can define another problem associated here. We have this field data, our numbers of the epidemic, and we wanted to discover which parameters make this response closer to this field data. This is an inverse problem, and the formulation of this inverse problem is this: given some data and initial condition, find the set of parameters which minimize this distance here. To solve this, we employed a distribution reflexive algorithm, and here's the data we showed previously, and we fitted the model here. But in spite of we don't have it here, if you remember that first graph I showed with the number of suspected and confirmed cases of Zika, and by the words of some specialists, which was reported in the news during the year, we know that the peak, the blow up of the epidemic started in the month of February. In the top of the infection, the number of confirmed cases was around 3,500 cases each week, which is not what we see here. But we don't have, unfortunately, the official data confirming this. What was the solution we developed to try to improve this prediction, the calibration of this model? So we know extra official information that this peak must be here. We put a point that we call the ghost point for this information, and we obtained this other fit here. But it is over predicting the maximum. If we include the other 2 points, one before and one that after this one, we obtain a better fit of this one. This was the beginning of this research. For sure, there is a lot of uncertainty in parameters we obtained here. So, a most robust approach was considering these parameters not single values, but random objects. So, this is what we are doing now. We are considering the parameters of the model, random variables. In the consequence, the response is a random process, and we can not only give a curve, but an interval of confidence around the response. But as random variables, we need to associate the probability distribution for each one of these parameters. And an arbitrary choice is not a good way to start. So we're developing, we're calibrating, we're working now to calibrate this model using Bayesian formalism, Bayesian updating. And after we update this, we hope to propagate uncertainties to obtain not only nominal response, but interval of confidence around it. So what we did, what we concluded, what we expected to do in the future, we developed an epidemic model for the outbreak of Zika virus in Rio de Janeiro state. We calibrated this model using experimental data. The proposed model, from the qualitative point of view, seems to be right. The calibrated model fits well, but we need more. We need to do this calibration from the stochastic perspective. So this is what we are working on. We acknowledge the financial support given to this research by FAPERJ, CNPq, and CAPES. I acknowledge your attention. If you have any questions, I'll be happy to answer. Thank you.
We have time for questions, comments.
What's good about this model is that based on the parameters you estimate from the data, you can suggest to the public measures to face the disease. Do you have any kind of thought on that?
This is the motivation, but we didn't talk with any authority yet. We expected getting more confidence in our model before to say, we can give you some perspectives of the infection, you develop strategies to combat the propagation of the disease, or to orient your public action, your actions against this. But this is the point which motivates me in this.
Do you have any you planning to add propagation in space, like mosquitoes, nowadays?
Not in the first moment, we are considering time evolution for the moment. It's a good point for sure that it depends on the spatial configuration, but it's not our objective at this moment. Maybe if it evolves very well in the future.
Steve?
I would think also you might want to consider behavioral changes. If there's more infections, people may take actions to reduce their susceptibility to getting the virus.
I don't think I don't have your point. If
You know,
maybe we want to consider
when there's a lot of infection, people's behavior may change.
Yep.
So they may not go outside, or they may not come to Brazil, or something like that.
Yeah, for sure.
I decide to come anyway because I want to come. But so maybe some aspect of that could be put into the model too.
It can be improvement in the model, but we must include another group here. Some people are afraid to go to Rio de Janeiro. And we need to infer how this group interacts with the other groups. For sure it will not interact with this group, but maybe it can interact in some way with this. If you have any suggestion, we are open to this, among these interactions.
Well, I know. I mean, I frequently go to Miami, and there is the first real case of Zika is in Miami, and it's actually very close to where I work in Miami. But I see people there changing their behavior a lot, and they've actually taken extra measures to use extra control to kill the mosquitoes and that kind of thing. So there's all of those mechanisms that come into the equation.
Yeah, we can add mechanism of killing here, maybe the.
Excuse me. Where are you going to include the stochastic, the random part?
We have 7 parameters here: betas, alphas, gamma, delta, and number of people, the population. If we describe this as random variables, the response, which is a vector in R8, which has S, E's, I's, R's, and C, will be a random process. So each parameter will have its own probability distribution. We must infer this. We must construct this probability. We cannot say define it by it's a Gaussian.
I see.
We must obtain information and infer based on this information. And then this is our prior. We
Right.
can use this to put in the stochastic model, obtain a output distribution, and then refine this using the Bayesian.
Yeah, probably you are going to get better.
We fought some strategies to do this, but the problem, we have so little points. We have only 5 measures.
Yeah, what is
Every 2 weeks we gain another one more because the epidemic bulletin goes out every 2 weeks. No? Yeah. So, but we don't have here the region where this curve changes more. But I thought I thought in using the calibrated model here and as a synthetic data. Use this perturbed with white noise behavior, and use this to try to better improve the Bayesian.
right? Actually, this kind of model you are using is based on ordinary differential equations. Is there anyone based on
Partial differential equations, the suggestions of Flavio, but it's
Could
much
be-
more complex. It's
could
much
be
more
much
complex.
better.
We're not thinking using this type of model for the moment.
Another way you can do is maybe using automata, several automata models.
We use it for dengue.
What?
We used cellular automata for dengue. Dengue
Yeah,
You use
so,
for data?
yeah, that's it. So we can validate your model coming from this ordinary.
So just in comparison with the per model.
Yeah.
We can discuss this.
Okay, so very good. Okay, thank you very much for all the
Thanks for the
speakers.
first.